In the previous videos, I showed you how the main trusses work. The standard truss, the girder truss, and the gable end truss. In the following videos, I'll explain how to use each of the secondary trusses, along with all of their properties. Secondary trusses are responsible for transferring roof loads either to the main trusses or directly to the load-bearing walls. These trusses include hip trusses, jack trusses, creeper trusses, and valley trusses. At first glance, most of these trusses share the same parameters as the main trusses, such as roof pitch, chords depth, webs depth, and truss thickness. As you may have noticed, the only parameter that is not included here is the truss span. In these families, the truss span is defined as an instance parameter, which means it can be modified independently for each truss in the model. This makes sense because secondary trusses are mainly used to fill spaces created around the hips at 45-degree angles, resulting in different truss lengths. I'll start with the most common secondary trusses, the hip truss and the jack truss, which are very similar to each other. The hip truss is placed at the intersection of roof slopes, usually at a 45-degree angle. As we saw in the first video of this tutorial, when I drag this truss into the model, it is already oriented at 45 degrees. Unlike the main trusses, the insertion point of these trusses is not located at the center, but at the point where the truss rests on the walls. The hip truss sits at the corner of the walls, while the jack truss is placed on the face of a load-bearing wall. Because of this behavior, we can adjust their lengths without losing their correct position in the model. In fact, just like we did in the previous video with the main trusses, I can align each truss to the wall and lock it in place, so that if the wall moves due to a design change, the trusses will automatically follow. Jack trusses have a single alignment point, while hip trusses can be aligned to both walls that form the corner. This means that when the wall configuration changes, these trusses won't shift out of position. Only their lengths will need to be adjusted. When it comes to type parameters, we can also link the roof pitch parameter to these trusses, so that if the roof slope changes, the trusses update automatically. We already saw this behavior in the previous video. One interesting detail about the hip truss family is that the roof slope does not behave exactly the same way as it does in other truss families. Let me show you what I mean. If I measure the slope on this side, we can see that it is 22 degrees. If I measure it on the other side, it is also 22 degrees, which matches the value we defined. However, if I measure the slope right at the intersection of both roof planes, the resulting angle is no longer 22 degrees. But this is not an issue. The hip truss family already accounts for this geometric condition and automatically calculates the correct angle to compensate for it. Because of this, you only need to define the roof slope once, without worrying about performing any additional calculations manually. The next aspect we need to consider for these two families is the connection angle with the main truss, or with any other truss they connect to. If we select the jack truss, we can see that within the construction category, we can control whether or not the eaves are included. We can turn them on or off and also modify their length, just like with the other trusses. In addition, we have one miter cut parameter for the top chord and another miter cut parameter for the bottom chord, and these can be modified independently. This is important because in some cases, the truss connects perpendicularly to another truss, while the top chord extends to a different element where it may connect at 45 degrees or not. In other situations, the opposite can happen. For this reason, the top chord and bottom chord's cut parameters are handled separately. In the case of the hip truss, the behavior is slightly more limited. This truss always connects at a 45-degree angle, so the bottom chord only supports this type of cut. The top chord must also be cut at 45 degrees. However, in this case, you can choose using this option, whether the cut is applied to one side or the other. As you continue modelling roofs, you'll quickly recognise which option is required in each situation. Now that we've seen how the connection angle works, let's connect these trusses to the girder trusses. To do this, I'll go to the structural plan. I'm going to align the jack truss to the centre of the roof ridge. If you select either of these two families, you'll notice that they have 3 blue arrows that allow us to modify their dimensions. The first arrow is used to ensure that the truss is placed correctly on the wall. The second arrow controls the distance to where the bottom chord connects. In these two cases, that connection will be made to the girder truss. I can simply drag this arrow directly to the centre of the girder truss. Remember that in the previous video, I mentioned that from a structural standpoint, the simplest approach is to use the same thickness for all truss members. This is exactly where that concept becomes important. In this case, all the trusses have a thickness of 35 millimeters, so the family automatically accounts for this thickness and applies it to the bottom chord cut. If we look at this connection in a 3D view, we can see that even though we extended the truss to the center of the girder truss, the connection stops cleanly at the panel without requiring any additional manual cuts. Back in the structural plan, the third arrow controls the extension of the top chord beyond the girder truss. Unlike the previous one, this value is not fixed and depends heavily on the specific roof configuration. The hip truss works in a very similar way, but there is one important detail you need to keep in mind. To explain this, I'm going to place a new hip truss and rotate it using the spacebar so I can position it in this lower left corner. If I select the truss now, you'll notice that the dimension arrows are pointing in the opposite direction. In other words, the girder truss is located on this side, but I can't move this arrow toward it. In this case, there is no control button that allows us to mirror an element at a 45-degree angle, so we need to mirror it manually. To do this, select Mirror by Drawing Axis, make sure the copy option is turned off, and then select the roof diagonal as the mirror axis. With this, the truss stays in the same position, but its control arrows are now correctly oriented. The next type of truss we're going to look at is the creeper truss. Creeper trusses are smaller trusses used in confined or irregular spaces. Here I have 3 variations, which I call creeper truss, creeper variable truss, and creeper truss at corner array. I'm going to place the standard creeper truss near the hip truss at the top, and then switch to a 3D view so we can better understand its geometry. As you can see, this truss is made up of just 2 timber members, which are usually so short that they don't require diagonal elements. These trusses include all the parameters we've already covered for the previous trusses. Truss span, whether or not to include eaves, and their spacing. And because these trusses always connect to hip trusses, they will always have a 45-degree cut at the end. If, as in this case, the cutting angle is not oriented correctly, we can simply go to the plan view and use the mirror controls to correct it. It's that simple. Now, as I mentioned earlier, this type of truss connects to the hip truss, and in most cases, it does so on both sides. That's why I created this family, which allows you to place up to 3 creeper trusses at the corner of a hip truss. To do this, I use the corner array creeper truss family. I simply drag and drop it into any corner where a hip truss exists. Before proceeding, of course, I adjust the roof slope and the rest of the relevant parameters. This family also recognizes the thickness of the trusses, allowing it to generate the exact cuts needed to connect correctly to the hip truss, as you can see here. And while we're in this view, if you select the entire family, you'll notice that within the construction category, you can modify the number of trusses in the array. This value can range from 1 truss per side up to 3 trusses per side. This is very practical in most situations. However, when symmetry is broken, you'll need to use the simple creeper truss family to fill these gaps with individual trusses. Finally, we have the creeper variable truss, which can be thought of as a hybrid between a jack truss and a creeper truss. It doesn't include diagonals, and unlike creeper trusses, the top and bottom chords can have different lengths. Notice that the standard creeper truss always has the same length for both the top and bottom chords. That's precisely why the creeper variable truss includes a vertical member, allowing it to adapt to different connection conditions. The next truss we're going to look at is the valley truss. Valley trusses are used when you have a secondary roof perpendicular to the main roof, creating what are known as valley lines. In this example, you can see that for this secondary roof, we can place a girder truss here and even a couple of standard trusses that extend up to the load-bearing wall of the main roof trusses. To properly connect these two roofs, we need to place valley trusses in this area, which rest directly on the standard trusses of the main roof. Continuing with the separation of truss types, the first valley trusses I'm going to place belong to the standard valley truss family. These are made up of 3 triangular elements with a vertical member in the center. I drag the truss into position using the center of the ridge of this secondary roof as a reference point. When I select the truss, you'll notice that there are 2 blue arrows on each side that allow me to adjust its dimensions. If I drag one side of the truss to the valley line, the other side moves automatically as well, since both sides must remain symmetrical. Next, I'll generate a section view to see how the truss is behaving vertically. In this section, when I select the truss, we can see that it's placed on level 1. This is the same level where all the other trusses are located and corresponds to the top of the supporting walls. However, the truss doesn't appear to be sitting directly on this level. In fact, there's a gap between level 1 and the base of the truss. This happens because the first thing I usually do is assign the roof slope value, which makes the truss easier to configure geometrically. In this case, the slope of this secondary roof is different from the main roof. Here, the slope is 25 degrees. In the previous video, I showed how to use global parameters to control the slope of all trusses using a single value, avoiding the need to manually update each truss if the design changes. If you haven't seen that video yet, I recommend going back and watching it, since I explain that process in detail. If you have seen it, you'll notice that we can now create a new global parameter specifically for this roof. I already have a parameter called roof slope, so I'm going to rename it to roof slope main for clarity. Then I'll create a new global parameter called roof slope south. Assign it a value of 25 degrees and accept the changes. Next, I select the valley truss family, go to edit type, and link its roof slope parameter to the new global parameter I just created. The reasoning behind this workflow was already explained in the previous video, so I won't repeat it here. Now, returning to the section view, we can clearly see the distance between level 1 and the base of the valley truss. If I select the truss, I can use the blue arrow to adjust the vertical position of the truss. I do this because I prefer to keep the placement level of the family fixed to level 1. That way, if this level ever moves, the valley truss will move with it, just like the rest of the trusses in the project. Finally, I return to the plan view and copy the truss to its next position, for example, at 600mm spacing. I also move the section view accordingly and adjust the truss width again using the valley line as a reference. Then I return once more to the section view and fine-tune the vertical position using the blue arrows. In the 3D view, we can now see how all the trusses are adjusting automatically. For this last part of the roof, using a full valley truss is no longer practical. So instead, I'm going to use a family called Mono Valley Member. I switch back to the structural plan view and drag the family into the model. I place it roughly aligned with the center, and then I go back and fine tune it using the section view. Just like the valley truss, this family, which technically isn't a truss but a single element, can be selected and its height adjusted using the blue arrows. However, before positioning it correctly, the first thing I need to do is link its roof slope parameter to the global parameter we created earlier. One thing to note is that this family name includes the word mono. That means that when you select it, you'll find a parameter called cut end, which allows you to create a straight cut at one end of the element. This makes it really easy to extend or trim the element exactly as needed. In this case, I simply adjust it until it fits correctly. Now, the last type of family I want to talk about is timber beams for roofs. Sometimes, instead of a truss, what you really need is just hip rafters or roof rafters. For example, in this exercise, we placed a hip truss at one end and another hip truss at the opposite end. But right here, we have a smaller hip condition. Since we already have girder trusses or other trusses underneath, there's no need to place another truss here. Only a hip rafter is required. That's exactly where these elements come into play. In the package, you'll find hip rafters and roof rafters, which are designed specifically for these situations. At this point, this would be the finished model. I show this final result in another video, where you can see how I model the entire roof in just a few minutes, and how I create the stud walls using Revit native curtain walls. Just remember that when you purchase the truss package, you also get this complete finished model, so you can use it as a reference in your own projects and better understand how everything works together. To watch the video where I build the full model step by step, click here. And with that, this roof design with wooden trusses course comes to an end. See you in the next one.